First of all, I need to say thank you for my PhD advisor, Professor Georgine, for the invitation and general hospitality to cover all my expenses from overseas. I'm from Hong Kong. At least you applied for it. Yeah. And I am from far away, the other end of the earth, so Hong Kong. And today I'm going to talk about exit problem with its PDE. It's a working paper with two collaborators with Han Yuecai in Jilin University and Gu Wang, WPI, who's sitting somewhere here. Thank you. And working paper means it's not completed yet. And if you find some mistake or any comment, you are always welcome, and we can put it into our final version. All right, so let's start. So this is outline. We are going to talk about what problem, so the topic, the setup in the first part, and then main result and application and summary. So the topic is very soft. It's just like first. It's very simple. There's no much things involved. So we think about if you invest some money and X is some underlying asset value, and you are going to take dividend at real time, and here G is a terminal payoff. Not payoff, it's reward, whatever. And you are going to have discount rate lambda. And then you are going to evaluate its expectation. And zeta is the maturity. And this, I will call that as Feynman-Katz functional. And usually it corresponds to, so we can expect the value function V is the solution of PDE. It's a linear PDE. So we are going to ask, well, is that true? So does V given by average of some random thing really solves the PDE? Of course, we have to specify what X is. X is, in general, we want to cover all failure process with generator L. So thanks for Professor Roger Lee introduced the Levy process and then Markov process with jump, all kind of things will be included here. And what is the terminal time, the maturity? So the terminal time is exit time from some given domain, open set. So I write it tau O bar X. So that means X is escaping from O bar. It's closure.
So you really want to exit the boundary?
Yeah, I want to.
If the boundary is still continuing?
No, it's just killed.
Okay.
Yeah. So this is the functional. It itself has nothing to do with after killed.
No, I mean then it's exit time from O, not O bar.
O bar. This is O bar. Yeah. There's slight difference, but we're going to take O bar. And I try to explain it clearly why I do not take O. It only, all right, so maybe it is a very subtle thing, but we can see. And there's Feynman-Katz formula, and we refer Professor Oxendo's classical textbook. I quote this book because this is the course. My first stochastic calculus course was taught by Professor Kosminski, a famous Russian mathematician, and he adopted your book. And even now, after 15 years, I still open that book and see, which theorem corresponds to which one in my paper, something like that. So I really appreciate the book. But this is different from the Feynman-Katz formula in your book because there, the terminal time zeta is not random in your book, right? It's just capital, and it's not bounded. So there's some here. It's some region. All right. Now I'm going to go through the talk with some example which I can explain to first year calculus student. So we talk about just one-dimensional unit interval, 0 to 1, O. And X corresponds to generator this. That means X is just T, this first order term corresponds to T, plus this is with volatility epsilon WT, and with some initial point. Now zeta is the time it's escaping from this unit interval. And the dividend is just 1 unit and no terminal reward. So this is V of X. We can even explicitly compute that by its density. And we usually expect its ODE. This solves this ODE. So the first part is negative L plus U. U corresponds to lambda. Lambda equals 1 we take for simplicity. And this is running cost, which is dividend. And boundary condition is because the terminal reward is this, 0, so we can just simply put 0. So the question, rephrase it from from general to special case is this one. So does it solve this? The answer is very simple. Yes, if and only if epsilon greater than 0. In other words, if epsilon equals 0, then it doesn't solve it. Why? Because explicit computation for epsilon greater than 0 is given by that. But if epsilon equals 0, V is given by this. Of course, you can take the limit from this general formula, and you'll come up with that. And if you calculate its interior point, it really satisfies equation. But at the boundary, V of 1 equals 0. That's fine. It meets the boundary. But V loses its boundary at 0 because V of 0 is something strictly positive number, right? It doesn't meet so it's quite counterintuitive. I'm not sure for me it is counterintuitive. So can we explain that? So here's one paper. So this is myself and Erhan. Recent paper partially answered this behavior. So it says if V solves PDE if following condition: all points at the boundary is regular to outside. Then you may ask, what do you mean by regularity of the point? Regularity, I will explain, but simply speaking, regularity means if you run the diffusion at the boundary, from the boundary, it immediately goes out. Then this is regular. Otherwise, it's irregular. So let's look at, so this is the definition. If X is regular with respect to L, if probability of X, so this probability is the probability induced by process set starting from small x. And so if epsilon greater than 0, then both 0 and 1 are, so suppose this is domain 0 and this is 1. Then both boundary are just 2 points. Both are regular because it's non-degenerate generator. It's Brownian motion always very naughty. It always jumps frequently. And if epsilon equals 0, so if epsilon equals 0, then what does it mean? It means there's no WT, just T. The process, if you run from here, it just goes this side, outside. This is regular, okay? But if you run run X from here, it's getting into the boundary. In other words, it doesn't go out. So this is not irregular. So that means we can explain that, well, if epsilon greater than 0, then okay, all the boundary points are regular. So this solves the equation. But it doesn't answer if epsilon equals 0, 1 is irregular, 0 point is irregular, then we do not have any answer from this paper. So we are going to, so what is the comment? So we satisfy viscosity solution property at x equals 0, which means, so this is the next slide. So here's what we can look, so we can identify. It is also just first year calculus course can deal with. So at epsilon equals 0, the function is like this. When v is look like this. And then at 1, it meets the boundary, but this guy gives us trouble. However, if you look at its viscosity solution property here, then it satisfies viscosity solution property. So x equals 0 is irregular and satisfies viscosity solution property. Therefore, V is generalized viscosity solution. So next slide, we will give you the definition. But just simply speaking, all right, so what is Dirichlet problem? Dirichlet problem means in interior point, those guys need to satisfy differential equation. At the boundary, you are going to expect this must satisfy boundary value given. But here, what happens is inside interior points, you can have differential equation. It satisfies that. At the boundary, regular points satisfies the boundary condition. But this boundary point does not do its job as a boundary point. It do the job as interior point. So this guy kind of cheating us. So how does it cheat us? So generalized viscosity solution, I first time I involved with that from user's guide on viscosity solution, and that time I couldn't understand, and later later gradually I understood what it means, but this is really simple. The definition means, okay, the same as strong viscosity solution, the first point, the requirement, the candidate function must satisfy the differential equation, in other words, viscosity solution property, inside the boundary, inside the domain. But at the boundary point, strong solution means you must satisfy boundary value. But here it's relaxed a little bit. You can either satisfy the boundary value or behave like interior point. This is what it means. So our goal, now we can be precise with our question, the original question. So original question is, does V solves PDE? Now our question is V a generalized viscosity solution of PDE? So this is precise question. Now we're going to reinterpret this definition. So a candidate function U, of course we have to require that continues up the boundary. A function U is said to be generalized solution if U satisfies viscosity solution property in O bar, which means closure. Closure set minus gamma out. Gamma out is those points which the function actually meet the given boundary. And if you are looking at the boundary points, if there is something left outside gamma out, then you have to verify its viscosity solution property, just like interior point. Now we have first sufficient condition. So we are going to answer that question. Is that question clear? I'm not sure. So very simple. Does V solve PDE in generalized sense? That's the question. So for that, we need to find sufficient condition. So we can find that if V don't know, V is just given by probability expectation of some random integral, right? So but we don't know its measurability, continuity. But if V is continuous up the boundary, then V is generalized viscosity solution. And we can also say something about gamma out. In other words, where you can expect to meet the boundary. So that gamma out can be considered as part of solution. You're not only interested in function value. So here, gamma out, where you can expect to meet the boundary, in O bar C means outside, complement of the closure set. And star means closure, of course, not Euclidean topology closure. It's the closure under fine topology. So O bar C star is fine closure of O bar C, which means, next slide. So, but in so let's consider that. So let's explain it. That so fine topology is kind of topology. So every time you want to define certain topology, you need to define. It's sufficient to define all the open set. So finally, we come up with what we mean by finally open set. So first, X is regular. We define X is regular for the set B if probability of X tau BC equals 0 equal 1. Let's take this example, the same example here. So we have this as A, and what is B? B is here. B is complement of O bar. So B is here. So all the regular point means it directly immediately get into B. In other words, if you have starting the process from here, of course it's already inside, so you don't have to worry. It's irregular. If you're starting from something, this is O, right? If you're starting from interior point O, then it takes some time to get out, right? So this is irregular. How about boundary? So if you run Brownian motion from boundary point, yes. Yes, we allow jump. But we only consider right continuous, right. So catalog path. Fellow process always have catalog version. Just the last slide you mentioned, right? So if you run Brownian motion or something like epsilon greater than 0, non-degenerate, then this guy immediately take out. This guy immediately take out. Both are irregular. So what is so BR means all regular points for B. In other words, what is B? R, all regular points. In this case, it's supposed to be from negative infinity, including 0, and 1 to infinity. And what is closure of B? Fine closure. It is union of this. In other words, this is the same in this case. Okay. In other words, this is the same as B bar. So if epsilon greater than 0, non-degenerate operator, then you have fine topology the same as Euclidean topology, at least for open set, right? But epsilon equals 0, then it gives something different, significant difference. What is B star? B star means including all the regular points, but we know that this guy is bad, very bad. So we need to take out from this. So this is parentheses if epsilon equals 0. So this is different. And we say that, well, what is gamma out? Gamma out is B star intersect with boundary B, Euclidean boundary B, which is 1, only 1. So this is the interpretation. And, oops. So can we stop here? But seems like given V, a value function, it's really hard to identify why it has to be continuous. which is assumption of condition, sufficient condition. And we find some example, which is counterexample, says that, well, it's a two-dimensional domain. I couldn't find one-dimensional domain counterexample. But two-dimensional domain, it's a rectangular domain. And even inside the boundary, V is just discontinuous. So it could be bad as much as you can expect. So in other words, we need, when we in CO bar, we need some additional condition, so we need to look for. So what is the main result? Main result is this. Partially answer your question. So we have to deal with O, okay, and O bar as well. So we define another stopping time, which is zeta hat, which is the process escaping from open set, right? And zeta is, if we recall, this is escaping from its closure. So the assumption says, when V is generalized viscosity solution of PDE, if it satisfies, if you're running from X, the process from X, then this X zeta hat is in O bar C star. In other words, you're running, maybe just like this is domain now. So you can run this and anywhere from X. If you go out, suppose this is regular part, this is irregular part. So this is regular part. Then it must, when it goes out, it must goes out from regular part. And before that, you never touch it. You cannot say something like this and this and this. Then this guy is bad. It gives some trouble. But this guy is good. So this condition actually tells restrict X for those process which, if it goes out, you should go out from regular part, and before that, don't touch other part, irregular part.
If X is on the boundary, that's part of the bad part of the boundary, that's already bad.
Say again.
If X is on the boundary, that's the bad part.
Yeah, bad part. This is bad part.
That's by definition it's bad because it does not satisfy.
Yes. Then we're not going to consider this. Yeah. So like the counterexample when epsilon. So epsilon. The counterexample. The real counterexample is this. So example 2, which is this. This guy actually touched the boundary before it really exists. Yeah. So that's the real. But epsilon equals 0 is not counterexample. Epsilon equals 0 for this case, for uniform when x equals just t, it is good example actually. It is generalized viscous solution, but not strong viscous solution. Right. So and we can also characterize when it meets the boundary. So the same, we explained that. So this is a small question. All right. So well, I am running out of time. So we can quickly go over that. So alpha stable process, which is subset of your process in the Markov jump process given by SD. Oops. So alpha stable process, let's have this. So J is alpha stable process, which is well known that it corresponds to a generator with fractional Brownian motion, fractional Laplacian. If alpha equals 2, then it corresponds to Brownian motion. And we look at dxt equals b dt plus sigma djt. B is constant, sigma is constant. In other words, x is Levy process, not even like space dependent. So we can directly write the generator here. And then we can ask, well, if given O, my question is when the boundary is regular, which points? Then the answer is, of course, O is bounded open set with exterior cone condition. So the answer is very simple. Either alpha greater than or equal 1. So just Brownian motion. If you run Brownian motion from boundary, then it's immediately take out. So like Brownian motion, alpha greater than or equal 1, then it behaves like Brownian motion pathwisely. If B equals 0, and if alpha less than 1, it may not be regular. It could be irregular. But if B equals 0, then there's some symmetric argument from symmetry of the distribution. We can say still like take out immediately. So these two gives regularity condition. Now we look at the non-stationary equation, which is usually called parabolic equation. So it depends. So here is if zeta wedge to t, minimum t, then it corresponds to this equation. We can actually think of this by just using change of variable as an elliptic equation, but sacrificing one dimension. So then this is elliptic equation, and get back to our main result, and we say, okay, if B equals 0, either B equals 0 or alpha greater than or equal 1, then this guy solves this from our main result on the elliptic case. So again, we are looking at nonlinear case. So we up to now, everything is linear, but now we can look at nonlinear parabolic case. Then this is HJP equation. Why? Because this is something like supreme of LU, and L is parameterized by some kind of B or whatever control, and something like that. So if gamma equals 1, you can directly write this guy as infimum of B times this. This is generator, linear operator, and B, it can be chosen. So this is HJP equation. If gamma equal greater than 1, this is called KPJ equation, which is very famous now, probably because the Martin Herrera proved the regularity structure for KPJ equation. But that one has different story. It has space-time white noise. So, but here, this is KPJ equation, deterministic KPJ equation. And also, you can use Lagrangian Legendre transformation to write it in the form of our classic Berman equation. So how does it relate it to stochastic control theory? Everybody should, I think, should be familiar with that. So when I prepared this slides, I'm just astonished. Wow, we only have a few attendants and invited so many big shots. So those are my favorite reference books about control theory. So let's see who's here. Jin, he's not here. Bern, Ken, George, Qing, not here. Xunyu, Jianfeng, 5, 6, 7, or what? So yeah, it's quite a few.
That's over 15. I think that's over 15, right?
Over 15, yeah. You're talking about machine learning. I'm also considering machine learning about this, but.
You have this list first, or you see the?
You can
this is somehow, yeah. If you give boundary condition, don't overfit. So if you give overfit boundary condition, so something like this. If epsilon equals 0, if you give two boundary conditions, that overfit, and really destroys your strong solution condition. So,
but you knew the list. You knew the list of the speakers, so they put that.
You did mind that's cheating.
yeah, I agree. It's cheating. I just added a few references last night. Sorry, but yeah. Anyway, so that is we can use our result on the linear together with comparison principle plus Perron's method to give a theorem like this. So we can give if alpha greater than or equal 1 or no. In this case, it's just solvable. It's just solvable. There's no condition needed. So that's pretty much everything. Thank you very much. So this is some.
Any question?
Yes.
You see
seems your boundary conditions has something to do with so-called entrance boundaries.
Oh yeah, that's again the same question